Go ahead.
All right. Well, we are really glad to have Dr. Lerch speaking to us today. He's kind of like the black sheep, the long lost child. He has a background in signal processing, but he's got other skills as well and is over in the music department. He's written a book on auditory scene analysis, auditory content analysis, audio content analysis, and does a lot of really interesting research. And I don't want to spend too much time because I want to hear what you have to say. So here's your microphone, and let's welcome Dr. Lerch.
Thank you. Yeah, thank you very much for the introduction. Thank you for having me. It's a great pleasure to be here. As I mentioned, I have actually been giving a talk like many years ago in this seminar, so it's good to be back in this library, I guess. So what I want to do today is I want to pick three projects that I have worked on with my students in the last 2-3 years, and that have one common thread, namely how to work on applied machine learning with a very limited amount of data, with relatively small training sets, or like in general insufficient data. So very quickly about myself, I do have an electrical engineering degree. I did a dual degree. I also have a Tonmeister degree with this kind of a music production, classical music production degree. And after my master's, I actually co-founded a company, and we did a lot of music software stuff, mostly in the licensing business, but always very close. It was a very research-focused company. We collaborated a lot with the Technical University in Berlin, and we prided ourselves in doing like state-of-the-art signal processing implementations for music. So today I want to talk about audio classification, and the first 3 slides are really this very broad layman introduction of this. So if we talk about audio classification, this is, I work in the field that is called music information retrieval, and classification is actually one of the really seminal tasks for this field. In the early 2000s, there were the first systems, or actually in the 90s already, with speech music classification and so on. And then in the 2000s, there were actually many people working on classifying genre, musical style automatically. And then moving further, there are other classification tasks like detecting what instruments are playing at what time in a musical signal, detecting the emotional content of a musical signal, doing automatic tagging for music signals, and classifying what artist is playing or singing, etc. So there are plenty of these classification tasks in music, and obviously there are plenty of audio classification tasks that are not music related. Just to name 2 non-representative examples, I guess, would be like speaker classification, or detecting audio events, or doing urban sound classification, something like that. So, and the first time I worked on this was actually nearly 20 years ago. And at that time, we had this very old school approach to solving these tasks. So we custom designed some features, and here we made sure, or we tried to make sure, that these features are a compact representation of the audio signal, are not too redundant with each other, are task relevant, of course, right? So it doesn't help to have a technical descriptor of an audio signal if it's meaningless to detect, for example, musical genre, if we want to classify that, and relatively easy to extract and to interpret. And then this was followed by this traditional classification theme. So we had Gaussian mixture models, support vector machines, and so on, and got our classification done. Nowadays, this is an example of a more or less typical workflow in audio classification nowadays. So we have this neural network-based approach. Very typical is a CNN architecture. That's nowadays a current, like like a baseline system for this classification. And the main difference here, obviously, to the previous approaches is that we do not actually design features. We do not actually put the knowledge or try to convey our knowledge in the feature design, but we try to learn these features automatically from data and then do the subsequent classification. So what we, let me remove that again. Okay. So the point when we do this is that we require much less expert knowledge on the music part, like designing features and so on. That is basically taken over by the machine learning part. But the systems themselves, they become way more complex, right? It's less controllable, less interpretable, and there's less expert tweaking. There's a lot of tweaking in the neural network part, of course, right? But this requires a different set of knowledge, at least. And this also requires a much more rigorous experimental setup requirements than we had before. But more importantly, it requires much more data. Yeah, so that is, I think, the crucial point here, that by using these increasingly complex systems, we need increasingly more data to properly train these systems. Otherwise, we run into typical overfitting problems and so on. And why does it not work anymore? Sorry. Okay, so generally speaking, by using machine learning for this, we just generate, have our data, and the data is really important because whatever we do with the data is actually kind of parameterizing the algorithm, the machine learning algorithm, not parameterizing, but I mean, we train with the data, so it kind of generates this model that then maps the input to the output. So whatever we do with the data or what kind of data we have, obviously is extremely important for the output. And especially in music, but actually generally speaking, I think that's true for basically all fields. We have these general challenges concerning the data, namely that the data might be noisy, there might be wrong labels. The audio data itself might also be noisy in certain aspects, but the labels might be noisy as well. In music, there's a typical problem of subjectivity. When you want to classify musical genre, then you actually have to think about, it sounds very intuitive, but you have to actually think about what does genre really mean? And is there a one class categorization that I can do for genre, or does it span multiple classes at once, and so on? What happens with genres that are not in the training set? How does the algorithm deal with that, etc.? So there's a lot of subjectivity in there. There are many taxonomies out there from Pandora and All Music and so on, all trying to define like an all-encompassing genre tree, but that is not. They all differ from each other, right? So there's no absolute ground truth there. An important problem with data is obviously also imbalance and bias. So let's say I want to classify music styles on Spotify, but then I'm interested also in classical music. Now, the amount of classical music streamed on Spotify is much, much lower than the amount of popular music streamed on Spotify. So if I want to build a training set, then I have to kind of think about the imbalance here and how I properly train my algorithm. But what I really want to talk about here is the amount of data that we have for training. We have not enough data for training. That is not exactly true. We have a lot of music, right? So we can actually download a lot of stuff from YouTube and so on. This is all good. So the music data itself is actually not scarce, although we might have problems sharing that legally. But the annotations can become a bigger problem, right? So the annotations are partly, they are relatively easy to collect. So you could, for example, say there are websites like Music Brains or so, where there are actually a lot of tags out there where users actually annotate music with tags and so on. So we get actually some decent amount of annotations, but these annotations are noisy and users don't always agree, or they don't use the same consistent naming schemes and so on. So there are all kinds of crowdsourcing problems with this kind of thing. And then what is really tricky is to get to detailed annotations. So with detailed annotations, I mean something like, let's say you work on a drum transcription system and you want to know at what points in time is the snare drum playing, at what points in time is the bass drum playing. In order to train a system for that, you need to annotate the exact time of every snare drum hit and every bass drum hit, right? And that is actually something where you need an expert for. You cannot just sit anybody in front of a computer and say, label this. And it's a very tedious and time-consuming task, even if you're an expert. So that means that for these types of annotations, we don't have much data because somebody usually has to pay someone else to annotate data, and there's a limited amount of resources for doing that, right? So that means this is a very typical problem in every detailed transcription task for music, that we have not super much annotated data. I mean, over the years, there have been many PhD students, and often as part of your PhD program, as part of your task that you're working on, you create a data set or you extend another data set and so on. So it's a continuously growing resource that we have in the field, but it's still outpaced by the data-hungry systems that we deal with nowadays. So, which brings me to the actual things that I want to talk about. I mentioned 3 projects to deal with insufficient data for training. First, this is kind of, let's say, I would say a more standard approach to deal with low resource classification, namely a semi-supervised approach for audio classification. This is very weird. Okay, there we go. And then secondly, the last 2 projects have been relatively recent, published last year and this year, with kind of more, let's say, novel ideas to how to deal with insufficient data. And now okay, now it works again. All right, so in this case, for the first project, I'm talking about music instrument classification as an example task. And here we have a relatively large data set for this. It's the open mic data set, but it has incomplete labels. And that means that we have these audio snippets, short audio segments, and we have labels for 20 instruments. Whether the instrument is in there or whether the instrument is not in there, or whether there is no comment on that. So we have labeled parts, positive and negative labels, and then we have actually a lot of unlabeled things. And these question marks, they can mean the instrument is playing or not, we just don't know. The users didn't annotate that. So, so that means the positive and negative labels, this is what we can easily deal with. This is a standard machine learning setup where we say, okay, yes or no. But then we have this, and we will see it's actually 90% of the data set that is not labeled, where we don't have actual labels for the appearance of these instruments. And then obviously the goal here is for this approach to utilize this unlabeled data to utilize these unlabeled data in some way to build a representation that we can still that is still powerful for inference for the actual music instrument classification. Okay, quickly about the data set. We actually did this with this study with 2 data sets. So this is the open mic data set that I talked about. We have 20 classes of musical instruments. It's always 10-second snippets. And the instrument can play anywhere in there, right? So it actually doesn't have to play continuously over the 10 seconds, but it's what we refer to as a weak label. So we don't know the exact time within the 10 seconds that the instrument appears. And actually 90% of the data are unlabeled in this data set. Then we have an urban sound tagging data set. So this is 23 classes of urban sound. So it's a dog barking or a car honking or whatever sounds you have in an urban landscape. And here we have 23 classes. It's also 10 seconds. Here only 6 labels, only 6% of the labels are missing, right? So this is nearly completely labeled. Okay, so for our experiment, first of all, we have 2 baselines. The baseline, first baseline is the trivial interpretation of the missing labels, namely, we treat the missing labels as negative labels. This is actually what surprisingly like 80 to 90% of the publications dealing with this data set do. They say if this is a missing label, then we treat it as a negative label. So this instrument is not in there. In the second baseline, we ignore the missing labels in the loss function, right? So this kind of makes sense. If we have positive labels, we have negative labels, and the labels where we are not sure about, let's not say this is positive or negative, let's just ignore that. So this is the second baseline. And then we have the first method to deal with the missing labels, where we actually have a student-teacher approach, or teacher-student. I'm not sure what the more common way is to refer to that. But what we, in a first step, assume is that all missing labels are actually negative. And then we train a classifier for that. And that classifier is referred to as a teacher system. And then we use that classifier to actually predict our missing labels. And we have a confidence measure for this prediction. And then we use the highly confident values predictions as a new pseudo ground truth and train our student system with these with this extended data. And then for the unlikely predictions, we still mask out the loss, so we don't let them impact our training. The second method that we tried is the mean teacher approach. So here what we do is, it's also a teacher-student approach in a way. So here what we do is our teacher is actually continuously updated while we are training the student. And the teacher is the average over all the previous student systems. So for each epoch, we actually update our teacher as an average over previous training epochs. And then the student is the current training result. And it's an exponential average. So systems like the weights that are very far in the past will not influence our teacher as much as the most recent weights. And this is, then we compute a so-called consistency loss, where we basically evaluate, okay, this average system, does it have the same prediction for my data as the student system or not? And we compute a loss from that. And when we train the student, we combine this loss with the actual cross entropy loss that we're using as a standard loss function. And then we can show, actually it has been shown by other people, you see the reference in the slides, that this actually improves training a lot, because it kind of avoids like dramatic changes in how the student system reacts to data. And we can And this is a very neat way, I would say, of adding this consistency to the loss function. Well, I already said that. Anyway, let's just jump to the results here. Actually on the left-hand side here, the left plot are the results for the OpenMic dataset, and the two plots on the right are two metrics for the Sony, the urban sound dataset. So what we see here, not really surprising, is that the first baseline, where we just treat our missing labels as negative labels, does not perform very well. What we do see is that actually just masking them out during training is already improving performance significantly, and maybe sufficiently even compared to the other results. But anyway, so we see that we already have here, for the OpenMic data at least, we have already a huge improvement, comparably huge improvement, by just masking out the losses for the unknown labels. And then comparing that, the label enhancing doesn't actually add much compared to the second baseline. But the mean teacher, the consistency loss, is actually increasing the results a little bit more. Then when we look at the urban sound data set, there are some imbalance issues actually in this data set, and we haven't really dived into that imbalance issue. So that's why we report the macro and the micro accuracy. So what you see here for the micro accuracy is that the results kind of follow the same trend that I described for the OpenMic dataset. For the macro accuracy, which is the averaging over the class rather than over the observations, we actually see that the standard teacher-student approach actually seems to perform very well. So I actually do not want to dive too much into this, but I think this kind of establishes the, let's say, the state of the art. This is how many people deal with these missing data, having these semi-supervised approaches or teacher-student approaches to solve this issue. One important reason why we use the Sony dataset is that it's nearly complete. So actually that also explains a little bit of the variance here. So we have only 6% missing labels in the Sony dataset. But then we could actually run an experiment where we remove training data from the dataset and see how the different methods perform. And what you see here is that the two simple baselines, they decrease rapidly when we remove training data, right? So the more training data we remove, the more the performance declines, while actually for the label enhancing and to a certain degree for the mean teacher with the consistency loss, we stabilize this a little bit more, which is obviously exactly what we want if we deal with low amounts of data. So that's an interesting observation. We were a little bit disappointed by the mean teacher here, I have to say. We expected a bit more in terms of stability for the if we remove more labels, but still, I think these are some interesting results about how to deal with missing labels in data sets. The second project is kind of representation learning. Also, I could phrase this in terms, although this is not by any means an area of expertise of mine, I could phrase this in terms of knowledge distillation. So what we do here is, or the question that we wanted to ask is, how can we provide extra training information? So we have a relatively small self-contained system. It's small, so we don't overfit too much given the data that we have. Is there a way to provide extra information to that system without actually having additional data labels or doing multitask learning. Or so these would be other methods to deal with that, but we don't have these extra labels, but we still want to kind of create a representation that is in some way more powerful. And the idea here is to use pre-trained features. So we have these huge models. VGG is one. It's a super deep ResNet that was trained on YouTube data, really many gigabytes of data, and it was trained for audio classification for urban sounds mostly. But it actually has been shown that these features that this model extracts can be easily transferred to other tasks. So there are a lot of music tasks that use these features. Similarly, OpenL3 is another representation or feature that has been very effective for a multitude of classification tasks on audio. So our goals here are now, we want to use these pre-trained features, and we want to impart this knowledge of these very deep networks in some way to our shallow model during training. And we want to improve the learned representation of the model. Another thing, another goal here for this particular approach was that we didn't want to use these features during inference. We only wanted to use these features during training, right? So the classical transfer learning approach would be, okay, we just take these features, we input them in a more shallow network, and that's basically it. Or we take the big structure here of our feature network, VGG network, and try to fine tune it in a way. So this would be the two typical transfer learning approaches. Here the goal set was actually, let's only use this really deep and also workload intensive network. Let's use this only during training, but keep the inference model independent of this feature extraction. So this is what we ended up with as a very broad flowchart. So up here would be the normal approach. So it's really a standard network. It's a CNN. It doesn't really matter what network architecture we used. The interesting thing is now that we have added the second path here, where here we extract these VGG or OpenL3 features from the input signal. We have our feature, and now we want to modify our embedding utilizing this additional feature. So we have basically, again, a combination of loss functions that we deal with here. So we have our normal loss function from that comes back from the output, which is usually cross entropy or something like this. And then we have a second loss function that we compute with the help of these additional features. And we use two approaches here. Method one is we actually try to force our embedding space to have a similar structure as the VGG features. So that means that we really try to we just directly compute a distance between the features, between the embedding space and the external features, and we try to shift the embedding space so to look as like a VGG feature a little bit more. And then the second method would be only a distance-based optimization here, where we force the distances between pairs of our features in our embedding space to be similar to the distance of the external features. So this is a little bit similar to contrastive losses in some way. So these are the two methods that we try out, and we compare this to baselines. One baseline would be really to just take the feature, train a simple classifier head, and see how well that performs. I mean, train the feature. I don't mean train the feature. Use the feature VGG or OpenL3 and train a classifier head on that. And the second modification would be the second baseline to actually concatenate our embedding space with the additional feature. So we just extend our embedding space basically by this feature. So that would break this inference goal that I stated before, that we don't use these features during inference directly, but it's an interesting comparison as a baseline. And please interrupt me if I'm going too fast. Yeah, there's a. In this, I mean, you could try to update the weights, you could fine tune it, but in our case, it's fixed. Yes.
And then question on the previous slide, the conreg is casted regularization?
No, it's actually not. So here we try to really force the coordinates in the embedding space to be similar to the coordinates in the VGG or OpenL3 space. So that is kind of making the space look more like VGG-ish.
Yeah, you're trying to map the embedding spaces so they're exactly the same structurally. What is conreg?
Now you got me. It did make sense when we wrote the paper, but I don't remember what it actually meant. Yeah.
I have some intuition for essentially you're trying to learn the embedding very similar.
Well, we don't. So this is one loss, right? One of the two losses that we combine tries to make the embedding more similar to the pre-trained features. But we still have the other loss, and the other loss is directly trained task specific from a mail spectrogram input, right? So the VGGs you could see as more task independent general audio representation that is good for many tasks, but maybe not brilliant for a lot of tasks. And then we have our task specific loss that actually optimizes for the specific data that we have. But also this network is actually relatively shallow. So we just, if we had enough audio data, we certainly wouldn't need the extra features, right? Because then we would just train our network. We can make it a little bit deeper, so it actually learns more details from the data, and whether this is a powerful representation or not, it wouldn't make much difference. But at least the assumption that we had when we started this process is by using a shallow network because of the limited amount of data, but then trying to transfer the knowledge from these very deep representations to this shallow network, we can actually improve classifier performance. Does it make sense? All right. In this case, this is now two different tasks. Well, this is actually also audio event classification, again, an urban setting and so on. And this is music tagging, where we have 50 different, the most common tag classes. And we would just predict in a multi-label environment which tags would be set by users. Okay, so this is a table. Let me quickly unpack this. So the first line here is well, at that time it was a recent publication on these two tasks, on these two data sets. So this is kind of the state of the art, more or less, around that. And then what we see here is if we just use our baselines, we see how these compare, right? So, and we see this for the different features, VGG, OpenL3, and then we combine those two features. We just concatenate them, more or less. So what you see here is that, for example, VGG, if you just use the features themselves and you classify, it's decent performance, but it's clearly below the state of the art. It's not really surprising. And the same here for the other data set. What you can also see here is that if we just concatenate our external features and our trained embedding space, we actually get quite Sometimes improvement, sometimes not so much, but there's a trend here that this improves classification a little bit. And then if you look at our two methods here for actually combining the losses instead of just concatenating those, you see that this actually leads to a slight improvement overall, especially with the conrect method. So the two baselines cannot outperform the trained systems without additional features. Combining these two external features tends to be better. So obviously they contain some different information in their representation in some way. And we can actually improve the representation in the embedding space by doing this extra regularization. Now, again, I have to admit that the improvements here, whenever I see a table with 3 decimals, I always get a little bit skeptical, right? So ultimately, the improvements here are not overwhelming, let's say, right? But I think it shows an interesting trend, and I think it's a very neat idea that my student had there. And again, what is very interesting is how this actually scales with the amount of training data that we have. So here, I actually forgot which data set we ran this plot on, but basically we removed, here in this case, we removed 90% of the training data, and here we removed 10% of the training data on the right. And what you see is, so we have this slight improvement of the regularization, and you see also a trend, again, not as impressive as we had hoped for, but it is what it is. We see a trend that this regularization actually does not decline as fast with a decreasing amount of training data compared to if we don't regularize this extra. All right, and the last project that I want to talk about is reprogramming. So again, this is some form of transfer learning, but it's transfer learning without actually changing the model that we transfer the knowledge from, but only change the input and the output. So it basically combines ideas from transfer learning and from adversarial approaches. And the idea here is that we can actually use very large models from tasks where we have a lot of data, and then just modify the input to these models, and then map the output of these models, and actually can use these models for a new task. That leads to the point that our training actually does not have too many parameters because we don't update the huge network that we use. We only have a much shallower network at the input, and we only need to train that. And then we can utilize this unmodified network that was trained on a different task. So the idea here is, just a second. Again, we have a pre-trained model. So let's say this is, okay, maybe let's make an absurd example here. This pre-trained model is trained on images. And then what we do is we have a data input here. Let's say we have a spectrogram input, and then we train a network, this reprogramming network, that maps this spectrogram input to something that the classifier expects to know in some way. And then we let the classifier just output the class labels, and then we map the labels to our target classes for our task. Again, the important part here is that this can be kind of a black box model because we don't train anything there. right? We keep this completely unchanged. We only train the reprogramming and maybe the label mapping if we want to do this a bit fancy. Oh, come on. All right, again, we come back to the open mic dataset, music instrument classification. As a test dataset, we have our 20 classes of musical instruments and 10-second snippets. And then we use, as the pre-trained model, we use the audio spectrogram transformer, which is has been proven as a quite powerful model for audio event classification. And it provides like state-of-the-art performance. And then we do an ablation study. We have with comparable amount of parameters that we test. We have just a normal CNN. Then we have a units. I should have revisited this publication. I'm actually, I have to think about this. But then we have our actual reprogramming where we do the AST as the black box model. We have a CNN for input processing, and then we just have a fully connected layer at the output to do the label mapping. And we do the same for with a unit. So a unit structure is basically an encoder-decoder structure where we also have skip connections. That's why we depict it as a U. So unit is very commonly used for audio source separation, for example. It's a very suitable model for that. All right. So, and here, what we see here is all these results. So if we just use our spectrogram transformer and only map the output to the set of classes that we have, do not do any input processing, we get the 62 F1 here as an output. So that's just a good to know baseline. And we see that this, for some reason, actually the CNN was not very powerful. Maybe it's too small. We see that it's kind of the range that we have for just the shallow architectures that we run as baselines in this test. And then when we actually do the interesting reprogramming stuff here, where we add a CNN at the input or a unit at the input, we can actually achieve state-of-the-art results for this. So you see this on the table here. Again, the results are pretty close. So maybe I'm bragging too much, but it's a little bit higher than the 81% that we get for another recent publication on music instrument classification. So that means we can actually beat the state-of-the-art performance, but at a fraction of complexity, right? Because we only have a very small network. It's really only 3 layers for input, encoder and decoder with a unit. We have a very small network there with only, what's that, 18,000 parameters. And we can achieve state-of-the-art results compared to a model with at least 10 times more parameters. Or maybe even more, I don't remember. But that's obviously very cool. And so actually the idea for this reprogramming came from a student here, Huck, who works on reprogramming in the speech domain. So if you, the idea here is if you have a huge model trained on one language, can you use it for a different language, for example? Can you adapt something for people with accent, like speech recognition, and so on. So he just approached us to do this on music, and I was very skeptical, but I think it was a very cool, fun project here. And there's actually another publication coming up at the current ICASP for this year. And that's basically it. I'm over time anyway. Obviously, there are many different ways for dealing with insufficient data. We can augment the data, we can synthesize data, we can use transfer learning, semi and self-supervised approaches, and so on. And I'm always on the lookout for new ideas how to deal with this problem, and how to also another aspect of this is how to impart additional knowledge during training to networks. Like what we did indirectly with this representation learning approach. I presented like with the semi-supervised learning kind of a standard approach, and then the regularization loss and the reprogramming as two not so mainstream approaches for dealing with that. And all approaches, there are always different trade-offs between training complexity, inference complexity, and then classification accuracy, of course. So this concludes my presentation. If you have any follow-ups, please don't hesitate to reach out to me. Just a shameless self-plug, you can also look at my book on audio content analysis. It's actually if you access it through the IEEE Explorer, it's actually free if you do it from campus. So you can download the PDF for free if you want to. And yeah, that's it. Thank you very much for your attention. We had a question there, yes.
Go ahead.
Okay. In the self-supervised case, I'm wondering if the reason you chose to go with using the transfer learning, the trained features vector, instead of like directly using contrastive learning on the data you have, was the limitation on the labeled amount of data you mentioned.
So the question with the contrastive learning is, this is a multi-label problem, right? So it's not only one class at a time, but it can be multiple classes at a time. And we also, furthermore, we don't really know. We know that obviously if something is labeled as one class, that should be clustered together, but we don't know how far away the other classes are, like how they are ranked in distance. So how would we do that in contrastive learning, right? We could only do some kind of binary thing, but then the multi-label complicates that a lot.
So what I was thinking is, I'm not familiar with the type of data you're using, but I'm wondering if within each sample, if our class is consistent, even like if you don't know the tags or the classes, like if there's an instrument or multiple instruments that I don't know what they are, in a single recording, is that consistent throughout the 30 seconds or 10 seconds?
So it's no. So if you want, you talk about splitting the data, for example, right? The problem is if we have all the event classification, you have a 10-second snippet, and somewhere in these 10 seconds are no bugs. You don't know whether it's at the 3rd second or at the 8th second or wherever, right? So that means if you split it up, then the label actually might be incorrect, because the dog then might bar the whole 10 seconds, but you don't know that for sure. So here we come at this weak label thing that I mentioned, right? That we don't know exactly if this is an ongoing thing or if it happens only once or twice, and where, etc.
I have a question about what you consider small data in this domain. I'm curious, like the open mic data set, for example, like how many hours of, or if it's hours or tens of hours or.
Where was it? This is the wrong one. It's actually, I mean, it sounds actually quite big, right? So here we have 20,000 10-second snippets. But then we have labels for 20 instrument classes, and 90% of these labels are missing.
And then I had another question around the representation learning part. You characterized the results as maybe kind of disappointing.
Well,
I was
when you start a project and you always think, okay, I'm gonna revolutionize the world of machine learning. And then it's like 2% gain and so on. Yeah, so it's, I mean, obviously it's statistically significant. We ran these tests, right? But it's still a very tiny improvement.
I'm curious, do you quantify the inference performance on those data sets, or like the number of parameters that you had on the learn network? It seems like DGG-ish might be really large in terms of like using it during inference time. Just kind of curious what that, like the scale of.
Yeah, sorry, I don't have these numbers right now. And BTG is really painful to even run, just do inference on an older GPU. I mean, it works, inference training wouldn't, but it is a very deep model for sure. But I cannot give you the number of parameters.
For sure. Like, I'm just kind of curious if retraining a new model that is able to mimic the feature space of that is a lot easier to do, like inference on like when you're doing it for real, like you have similar performance in terms of accuracy, but maybe it would be better because you don't have to run this gigantic model.
Yeah, that was one of the objectives here, right? That we didn't want to use this very high complexity model during inference time. There are also a bit concerns about fine-tuning and how to do this, and whether you actually break a lot of things by trying to update the weights of these very deep models. So I'm not saying that these are not solvable or anything, but it also comes with challenges, let's say, to fine-tune. But yeah, I mean, fine-tuning, we actually ran experiments to compare the fine-tuned things for the spectrogram transformer. For the VGG, we just didn't want to wait for a couple of weeks.
For sure. Don't mind if I ask like one last question.
Sure.
So there's a lot of like the representation learning seems like you listen to a lot of audio at once and you output one embedding. Have you considered like sequence model where you might take smaller segments of audio and learn over a sequence of those?
So the spectrogram transformer actually does that, right? So basically what you do is you have a spectrogram and it's attention based, obviously it's a transformer, right? So it actually puts the attention on different little spectrograms that you have at the inputs. So in music classification tasks, if we have these data sets that are only snippets, like here we have 10-second snippets and so on, we usually don't choose a recurrent structure for this kind of thing. It makes more problems than it helps for these snippets, because there we can just input the whole snippet in some representation and do the classification at once. Now, if you deal with longer sequences, then things obviously change, especially if you deal with sequences where the length is not predetermined, because then what are you going to do really? So then you end up with some kind of recurrent structure. It's very task dependent. So it always seems like some kind of sequence model should be better at modeling music in general, right? But it turns out it's actually very tricky to really capture these long-term structural properties of music that you would think about that should be captured, right? So ultimately, most of the recurrent models that work with audio, I mean, with course it's a little bit different, but with audio, they are good at capturing this local context, really, but these longer term structures that would actually help with a lot of music tasks, they are often not able to capture.
Great, thank you.
Yes.
So in the reprogramming approach that you showed, is the label mapping another neural network?
So this is yes. So neural network. It's just a fully connected layer at the end. So it's really just a linear combination of the outputs. We actually tried out something fancier as well, but it really didn't improve results at this output stage. This is dependent a little bit on the number of classes the source class had and the number of classes that you have, right? So if the big pre-trained network actually has only a few class outputs, it might become difficult to actually map this properly, right? Because if you have 20 classes and the model was trained on only 3 classes, still you could theoretically map this in some way potentially, but it's making things a lot trickier. So usually what you look for is the source model has a lot of classes that it classifies in, and then you map this to a lower number of target classes.
And in the teacher student model that you showed, so is the output like a weighted combination of teacher and the student, or is it like only the student?
You mean the consistency loss thing?
Yeah.
So the loss is a combined thing between the normal cross entropy loss and the consistency loss, which is basically how well aligned the student output to the teacher output is. So the loss is combined here, but everything else is untouched really.
So when we predict, do we predict using the student network? Or
Yes. So during inference, so this was only about training. During inference, we only use the student. Yes. So the teacher is not there anymore. Yeah.
So I don't know too much about this domain. So I naively thought in my head, doesn't a saxophone sound similar to all other saxophones? Why could this be hard? But then I saw your results and I was like, oh, this is hard. What is causing like the big distributional differences in like your application space?
So, I mean, you are right that the saxophone sounds similar to other saxophones. However, there are also vast differences between saxophones, right? If you have like, you have different types of saxophones, different playing techniques, and so on, right? So even within one saxophone, you have a lot of variation in terms. But the main issue is really that you have multiple multi-timbral instruments playing at once, and they are harmonically intentionally overlapping, of course, right? So it's not like we're often with speakers, if you do source separation or something like this, you have this assumption that you have like kind of separated spectra, right? I mean, it's often they are overlapping too, and that complicates things, but generally you assume like different pitch ranges and so on, and that makes the task easier. For music, the different sources actually intentionally play like sounds that are overlapping, right? With respect to pitch and harmonics and so on. And obviously then that makes it very hard to analyze or separate actually the signals because of this additional intentional overlap.
So I didn't so are these like these data sets, is this multi-label classification that's happening?
Yes.
Oh, I didn't get that. Okay, yeah, it's very hard.
Right. So this is all multi-label classification because for each snippet, we don't know during inference, we don't know how many of the 20 instruments are playing.
Yeah.
And whether they're playing at once or after each other or whatever. So this is all unknown.
Follow up to this question, could you speak to the quality of the sensors and the distribution of where the sensors are located? Does that also impact
The quality of what?
the sensors, how you're recording the sound?
Oh, well, so this data set was actually collected from, so the audio sources was collected from YouTube.
Oh,
this case, it's actually a little bit noisy because they did mechanical Turk for annotation. So they ask users to only label the instruments they are sure about and leave everything else alone, which is why we have so many missing units. But that also implies that the audio quality is very diverse, right? So whatever people put on YouTube, I guess.
Is it hard to generalize the distribution of one instrument from different genre? For example, if you have guitars in different genre that they play maybe with different speeds and different ups and downs and things like that. Is it hard to generalize for the distribution of guitar?
Well, guitar is very hard actually because you have acoustic guitar, you have distorted electric guitar, you have various effects that people put on guitars and so on. You have distorted guitar as well. So obviously there are some genre-dependent trends that you can observe, right? So obviously you won't have much acoustic guitar in thrash metal or something like this, right? So you can make assumptions about this, but the finer you get with making these assumptions, the less they are true. So for guitar, there's actually really a wide range of possible sounds. And with music instrument classification, what you also see is you have classes like synth. And this is a horrible class, right? Because it can mean any electronic sound. So it can also theoretically mean a sound that is supposed to sound like a clarinet, but is actually electronically generated, and so on. So it's all a mess.
I have a question about the reprogramming part. So you said you have the reprogramming network and the combination. So do you have to conjointly train their weights? And how would you do that if you have a black box in between?
So yeah, okay. So I kind of simplified this. So ultimately, what you need to do is you need to actually do backfactor gradients through the black box. So it's not really a black box, right? So
it's not alternating the weights of the
no. So this exactly this remains completely unchanged. That's the point.
You backtrack the gradient.
Yes, you have to backpropagate in some way. So that it's not that much gain actually, as I implied, maybe workload wise. Okay.
There are no questions.
There was one more.
Oh, I was kind of curious, what's the difference between reprogramming and like reinforcement learning?
Oh, that's actually is a completely different field of machine learning. So for reinforcement learning, and please correct me here if somebody knows this better than I do. But the point is that for reinforcement learning, you don't need a differentiable loss function, but you actually create you create kind of a reward function, and then how do I'm not good at representing reinforcement learning in 2 sentences. Does anybody want to take over here? Anybody working with reinforcement learning? Let's just say it's a completely different learning strategy that works differently than everything that I presented here with respect to loss functions and so on.
I actually see some similarity between your reprogramming method and your representation method. Because in both, you kind of have like a learnable encoder that learns the representation that kind of matches, a pre-trained model, and then which gets put into a decoder for the final prediction.
In a way, I can see that, yeah. So basically, what we train here is how can we make an input representation in this case. So it's not an embedding space representation, but an input representation. But how can we optimize an input representation that it works well with this pre-trained thing for this specific task?
Is that learned input representation interpretable? Like
No. Well, I mean, it's actually an interesting question. we haven't looked too closely at this. So in this case, we still have a spectrogram. So the source system was actually already an audio spectrogram. So it's not a completely different task that we take this from. So I don't actually expect this to look completely different, but theoretically, what we also wanted to try is something completely wild, like having a just an image classifier in the middle, and then try to make our spectrogram looking more like any image that can be classified, like a kitten, for example. I'm not sure if that really works. I don't think so. The idea here is not to make this interpretable, right? So actually, the early attempts for reprogramming, they just add noise to the input. So they have a trainable noise that they add to the input that maps from their target task to the source task. So it's really only making the model, the pre-trained model, think that this is some meaningful data. It's not about making the data meaningful.
So in a representation learning, there are two different ways of measuring the source domain and target domain, right? One is to measure the difference between distance between the feature, and another one is measuring the difference between the feature space. But I'm just curious about how do you measure the distance of two different spaces?
Well, so you mean because they have different dimensions?
Yes.
Yes. So the distance measure is just in this case, we use the cosine distance. So it's actually dimension independent. Right?
I don't quite get it, because if you want to measure the cosine difference, you still have to like have an inner product and the norm of two vectors, right? But if they have a different dimension, how do you perform the inner product?
Oh, okay. I was talking about, let's go to this. All right, I was talking about this. So here, this is actually, here is for the second method, it's dimension independent the distance because you have pairs, right? For this method, we actually have a mapping to a similar dimension of the features to be able to compare distances there.
Okay, thank you.
Any other questions?
Any online?
Thank you.
Well, yeah, thank you again for coming. We'll have more CSIP seminars next week in the future and for the rest of time. So, yeah.
If any of you are interested in working with music, feel free to reach out to me. I'm happy to discuss.
That was great.
Yeah.